Hello everyone, my name is Yu Kun from Department of Computer Science and Technology, King University, and today I will present our work entitled Evaluating Automatic Speech Recognition Models. How well do they handle accents? Conducted together with my teammate Liu Wei, under the guidance of Professor Hu Bin and Professor Diane Huak. The basic structures of this presentation is as follows. First, I will introduce the background and motivation of this project, and then we will talk about the methods that we used. Then I will explain our results, discuss the results, and finally talk about imitations and future works. Before introducing our project, I need to give you some background. Over the past decade, ASR has become an integral part of our daily lives. Whether we are speaking to virtual assistants like Siri or Google Assistants, using speech-to-text tools for transcription in business and media, or relying on accessibility tools that support those with disability. ASR technology plays a crucial role in bridging communication between the humans and the machines. However, despite remarkable advances in deep learning and end-to-end ASR models, a major problem remains unsolved. ASR systems will struggle to accurately recognize speech with different accent and linguistic features. This issue is particularly important in a globalized world where English is spoken with diverse pronunciations, rhymes, and phonetic patterns. Research shows that most ASR systems are trained primarily on standard delay lattice, especially American or British English, leading to significantly higher error rates when handling non-native or regionally assisted speech. For instance, Jian et al. Found that the world error rate of ASR models differs notably between native and non-native English speakers. Other studies have attempted solutions through methods like verb spatial adjustment, pronunciation dictionary adaptations, and accent adaptive modeling, but these efforts are still far from achieving equitable recognition for all speakers. This study adjusts that gap by evaluating multiple ASR models, cloud-based, local, and mobile, across datasets specifically designed to test accent variations such as speech accent retrieval (L2 ARC-TIC) and the India accent dataset. Through this, we aim to understand which models handle accent diversity best and where the greatest weakness still lies.
Now, let me tell you about our method. The workflow outlines the evaluation process to compare word error rate (WER) for different ASR models. It starts with various speech datasets, where audio files are pre-processed and the transcript use multiple ASR models such as Google Web Speech, DeepGram, and others. The generated text is then compared with the reference text to calculate the WER. The analysis focuses on comparing WER across different models and accent to gain insight into the accuracy of ASR system. To evaluate how well different ASR models handle accent English, our study uses three publicly available datasets, each chosen to represent a range of non-native English accents. The first dataset is speech accent retrieval, sourced from Kaggle. This dataset includes recordings of English speech from speakers in 11 different countries, such as Arabic, Chinese, Hindi, and more. A key feature is that all speakers read the same English paragraph, which allows for a controlled comparison of how ASR systems perform across different native languages. The second dataset is L2 ARC-TIC, developed by Texas A&M University. This dataset is specifically designed to analyze non-native English speech. It includes speakers from 6 language backgrounds, such as Chinese, Arabic, and Hindi, who each read phonetically balanced sentence. This structure allows us to closely examine how ASR systems respond to constant pronunciation differences among non-native speakers. Lastly, we included an Indian accent dataset, also sourced from Kaggle. It focuses on Indian English, which is known for its distinct phonetic patterns and rhythms, characters, given the size of original dataset. We randomly selected a subset for testing, ensuring a manageable but still meaningful sample.
Emphasize how different ASR systems perform with Ascended English. We selected 9 speech recognition models, which we grouped into 3 categories based on how they are deployed. The first group includes cloud-based ASR APIs. These are commercial services that rely on powerful servers and deep learning technologies to provide high accuracy transcription. In our study, we test Assist by AI, Read AI, DeepRAM, SpeechMatic, and Microsoft Azure. Each of these platforms use advanced neural architectures and supports various speakers, environment, and accents. The second group is logical run ASR models, which operate offline and are often used in open source or research applications. We selected Mozilla Deep Speech, which is based on Deep Speech 2 architectures and use RNNs, as well as OpenAI's Whispers, a multilingual model known for its rapidness across language and accents. These models allow more control and customization, but may vary in performance based on training data and hardware. Finally, we test built-in ASR systems, which are natives integrated into customer devices. This includes the Google Web Speech API, commonly accessed through browsers, and Apple's iPhone Speech-to-Text, which runs directly on iOS devices. These systems are widely used in real-world applications, making their performance exceptionally important for particular everyday use. After deploying these models locally and then using the dataset I mentioned earlier, we got the result. This is the first figure. It shows us the average WER of ASR models for speech accent attribute dataset. It provides a delayed breakdown of WER across different native languages, offering insight into how ASR models perform when confronted with diverse linguistic influence. A key finding is that Asian Standard English, particularly from Vietnamese, Chinese, and Korean speakers, result in higher WER compared to Europe Standard English from speakers of German, French, and Italian. This suggests that ASR models have been predominantly trained on Western Standard English, making them less effective for Asia language speakers. DeepRAM, OpenAI Whisper, and Assembly AI demonstrate relative stable performance across different accents, indicating that they are trained on more diverse datasets. However, Microsoft Azure and iPhone speech-to-text inhibit higher WER for specific languages, such as Arabic and Vietnamese, further emphasizing that certain ASR models struggle with linguistic diversity. The overall findings confirm that while deep learning-based ASR models have significantly improved performance for extant speech, challenges still remain in effectively processing speech from underrepresented linguistic groups. The overall finding confirmed that while deep learning-based ASR models have significantly improved performance for extant speech, challenges still remain in effectively processing speech from underrepresented linguistic groups. This is the second figure. This figure presents the WER combination for different ASR models on L2 ARCTS dataset, which consists of non-native English speakers from various linguistic backgrounds, including Arabic, Chinese, Hindi, Korean, Spanish, and Vietnamese. The results clearly indicate that Mozilla Deep Speech performed the broadest. with WER exceeding 95% across all accents, suggesting that this model lacks the ability to generalize it to non-native English speech. In construct, cloud-based ASR models such as Ensemble AI, OpenAI Whisper, and the DeepGram consistently achieve lower WERs, highlighting their superior ability to process accent speech. Rivi AI and Microsoft Azure, while offering moderate performance, struggle with certain accents, particularly vitamins to the Google Web Speech API and the iPhone speech-to-text also exhibit a relative high WRS, indicating the built-in or API-based solutions are not as effective in handling non-native speech. This overall trend suggests that modern deep learning ASR models trained on diverse datasets perform significantly better in handling linguistic variability. This is the last figure compares ASR performance across different datasets, namely the speech accent achieved, L2 ARCTIC, and an Indian accent dataset. The most striking observation is that WER for the Indian accent dataset is significantly higher across all models, indicating that Indian accent English presents a considerable challenge for ASR systems. The REV AI performed particularly poorly on this dataset, with WER exceeding 18%, while even the best performing models, such as DeepRam and OpenAI Whisper, struggle to achieve reasonable accuracy. The L2 ARCTS TIC dataset also shows higher WER than SAA, which aligns with the expectation that non-native English speech introduce additional complexity for ASR. Notably, Mozilla Deep Speech continued to perform poorly across all datasets, reinforcing the idea that it is not well equipped to handle accent or non-standard English. In construct, Ensemble AI and DeepGram maintain relative low WER increases between SAA and L2 ARCTS, demonstrating their relevance in recognizing speech from speakers with varying linguistic background. In construct, Ensemble AI and DeepGram maintain relative low WER increases between SAA and L2 ARCTS, demonstrating their robustness in recognizing speech from speakers with varying linguistic background. Having talked about the result, let's move on to the next part, discussion. One of the most important takeaways from this study is that not all accents are treated equally by current ASR systems. Our result clearly shows that speakers with Asian accents such as Vietnamese, Chinese, and Korean consistently experience higher word error rates compared to those with Europe accents like German, French, or Italian. This suggests that many ASR models have been trained predominantly on Western access English, which created an invisible bias against non-Western speakers. The Indian accent in particular causes the highest error rate across all models, even among the top performing systems. At the same time, not all ASR models are created equal. Legacy models like Mozilla DeepSpeech struggled across the board, with error rate exceeding 95% in most cases. On the other hand, modern deep learning-based models, especially Ensemble AI, DeepGram, and OpenAI's Whisper, performed significantly better across a wide range of accents. Their relatively stable performance suggests that they are trained on more diverse, multilingual datasets, making them more adaptable to different linguistic patterns. But most importantly, word error rate is not just a technical metric, it reflected something much deeper, real-world inclusivity. If a person's voice isn't accurately understood simply because of their accent, it means that wireless technology is sometimes designed to empower communication in unintentional, including entire groups of users. As ASR continues to be integrated into education, healthcare, customer service, and accessibility tools, this issue becomes more than technical, it becomes ethical. Now we move on to the final section, limitations and future work. About the limitation, while the datasite uses SAA, L2, ARCTSE, and Indian accent datasite represent a range of accents, they are still relatively limited in scope and quality. Many global accents and linguistic variations remain underrepresented. And then, most of speech samples are script or read speech. This does not fully reflect real-world usage of ASR systems, which often involve spontaneous, conversational, or noisy environment. Moreover, the study relies solely on word error rate to evaluate ASR performance. Other important dimensions such as latency, robustness, and semantic understanding were not assessed.
About future work, future research should include panelists and aesthetic speech to better evaluate ASR systems under real conditions, such as noisy backgrounds and casual conversation. A broader inclusion of regional accents, dialects, and non-English languages, especially in transcoding scenarios, and can provide a fuller picture of ASR's fairness and inclusion. In addition to WER, future evaluations should consider metrics such as statement error rate, real-time performance, user satisfaction, and error severity to more accurately reflect an end-user experience. We can also investigate transfer learning, domain adaptation, and accent-specific fine-tuning to improve ASR performance in low-resource or underrepresented accents. To sum up, this study investigates the performance of various ASR models in recognizing a certain English speech, using datasets that represent diverse linguistic backgrounds. The result revealed that while modern deep learning-based ASR systems, such as Inspire AI, DeepGram, and OpenAI Whisper, generally outperform traditional models like Mozilla DeepSpeech, all models exhibit a clear performance gap when transcribing non-native and regional accent speech, especially from Asian and Indian speakers. This finding highlights a presented bias in current ASR systems, likely stemming from imbalanced training data that favors standard or Western accent English. Our study also demonstrated that even the most advanced ASR models struggle to achieve consistent accuracy across all accents, suggesting that the current systems are not yet universally reliable for global users. To address these challenges, future work must prioritize grander linguistic representation in training data, adopt more robust evaluation methods, and develop adaptive algorithms that can better handle accent variability. By moving toward more inclusive and equitable ASR technologies, we can ensure broader accessibility and usability for users around the world.